Hello everyone, this is topic 15 and 16 part 2 for exam 4. This is topic 16, the binomial series. The idea here, here's a binomial function 1 plus x to the mth power, and we're saying m can be any constant. We know we could deal with one, m is a positive integer. For example, 2, 3, 4, etc. We could use the binomial theorem in Pascal's triangle. But what if m were to the 1/2 power? Then how do we deal with it? So what we're going to do is we're going to find the Maclaurin series. So remember, these are infinite polynomials. I'll put the definition up here. By definition, the Maclaurin was that the function f of x is f of 0 plus f prime of 0 times x plus f double prime of 0 over 2 factorial times x squared plus f triple prime of 0 over 3 factorial times x cubed, and so on. So now we're going to literally, like we did earlier, last lesson was by substitution, but here we're going to do it the old-fashioned way, and that's by the formal definition. And so we'll set up two columns as we normally did, one with the function. Actually, let me give myself a little more room because I think I want to move it a little more to the left. So one with the function and its derivatives, and then another one with another column with those evaluated at 0. So let's find some derivatives. So the general function 1 plus x to the mth, so it's a binomial function. We want to turn it into an infinite polynomial because now m is any constant. So think of m as a number, 5, whatever. If we were to differentiate, f prime of x would be swing down the m times the same variable quantity to the power 1 less than m, which would be m minus 1. And then the derivative of what's inside, but the derivative of what's inside is just, with respect to x, is just simply 1, so not necessary to write it. So that's our general power rule to differentiate. So then we'll need the general power rule again, so f double prime of x would be m, swing down, because m is just a constant here, so that's a constant multiple, it tags along, and general power rule again, swing down the m minus 1 times that same quantity, 1 plus x, power 1 less, m minus 2. And again, we should think derivative of what's inside, but not really necessary because that's just the derivative of x, which is 1 again. So let's just do one more derivative. So f triple prime of x would be the m minus 1 are constants, so that's constant multiples. They tag along in the differentiation process. General power rule again, swing down m minus 2, same quantity, 1 plus x, power 1 less, m minus 3. And then, of course, you can continue. So let's evaluate each of these at 0. So f of 0 would be 1 plus 0 to the mth, so just 1 to the mth, or 1. F prime of 0 would be m times 1 plus 0 to the m minus 1th. So that would be m times 1 to the m minus 1th. But it doesn't matter what m is. Take 1, raise it to any power, you're going to get 1. So that's just simply m. And so there's really no need to show that literal substitution for 0 anymore, because when we put a 0 in here for x, this is just going to become 1 to the m minus 2 power, and no matter what m is, 1 to any power is just 1, so we're just going to get m minus 1. And similarly with f triple prime of 0, we're just going to get the coefficient m minus 1, m minus 2. And you've got enough to establish a pattern. You can see what the next term is, right? It's going to be m m minus 1, m minus 2, m minus 3 would be a fourth derivative. Right, now we're substituting into the definition. So therefore, f of x would be, okay, up here, back to our definition of Maclaurin. F of 0 is 1, and then plus f prime of 0, m times x, then plus f double prime of 0, m minus 1 over 2 factorial times x squared, plus f triple prime of 0, m minus 1, m minus 2, all over 3 factorial times x cubed. And you can see the pattern there, how that would tell you that's enough to give you the next term. And so, in general, we're going to say that this function is, so in general, this function, 1 plus x to the nth power, expanded as an infinite polynomial, is this expression. Again, 1 plus mx plus m minus 1 over 2 factorial x squared plus m minus 1, m minus 2. Kind of silly for me to rate this step because it's just redundant. Sorry about that. Okay, so that's what that polynomial expands to be. Or there's another way to express this. As an infinite sum, 1 plus x to the nth is going to be 1 plus, okay, so we separate the 1 for a reason. The sum as k goes from 1 to infinity of, and then here's a notation that might be new to you. In a big set of parentheses, we write m on top of k, and it's read as m choose k. And it's really just the combinatorial coefficient, and then this times x to the kth power. And let's go further and say this is where m choose 1 is just m choose 2 is just this coefficient, m minus 1 over 2 factorial, m choose 3 is m minus 1, m minus 2 over 3 factorial. See, it's just the coefficients is all we're saying, and so on.